is a video solution to tutorial sheet 8. It has 7 questions. So as usual, I will go through every single one of them and give you a detailed solution. So just remember, this is on top of the typed solution that you have on the course website, right? Alright, so let's start with question 1. So you have three data points from a normal distribution with parameters mu and sigma squared, and these are 2 possible estimators for mu. 3 parts. The first part is to show that both these estimators are unbiased for mu. Right, so let's see how we can do that. Right, so this is question 1, part 1. So we want to show that both these estimators are unbiased for mu. So we need to show that the bias of this and the bias of the other one is both equal to 0. Alright, so okay. Now taking the expectation inside, okay. Now we know that each data has a normal distribution with parameter mu and sigma squared. So what you have is mu plus mu plus mu. Right. So we have mu minus mu, which is 0. So the bias of the first estimator is 0, right? Now let's look at the bias of the second estimator. Okay. Now take the expectation inside. You have a quarter, right? Okay, so this is going to be a quarter mu plus 2 mu plus mu minus mu, and this is clearly mu minus mu, so 0. So both estimators have bias equal to 0. So both estimators are unbiased, right? So that's the first part of question 1. Question 2, second part is to find the variance of the 2 estimators and say which one of them you prefer, right? So this is question 1, part 2. So let's try to find the variance of this, which is the variance of this. Take the 3 outside, it becomes a 9. Right. Now we know that each data point has variance sigma squared, so what you have is sigma squared plus sigma squared plus sigma squared. So it's 3 sigma squared divided by 9, which is sigma squared divided by 3. So this is the variance of the first estimator. Now variance of the second is this, right? And take the variance inside. If you pull out the 4 outside, it becomes 16. Then in brackets you have variance of x1 plus 4 times the variance of x2 plus the variance of x3. Right? Okay, now we know each of these guys is sigma squared, so it's going to be 1 divided by 16 times sigma squared plus 4 sigma squared plus sigma squared. Right, so this is 6 sigma squared divided by 16, which is 3 sigma squared divided by 8. Alright, so this is the variance of the first estimator, and this is the variance of the second estimator. Right, now we would prefer the estimator that has smaller variance. I mean, the smaller the variability, the better the estimator. Okay, so now in this case, clearly the sigma squared by 3, right, is less than 3 sigma squared by 8. So that means we prefer mu1 hat to mu2 hat. Okay. So that completes part 2 of question 1. Now part 3 is to what are the sampling distributions of each of the estimators. Now to do this you need to look at the video on the normal distribution. You may recall that one of the properties I discussed in that video is that any linear combination of independent normal variables, right, is also normally distributed, right? So one hat, which is a linear combination of independent normal variables, right, will have a normal distribution with the mean, which we worked out earlier, to be equal to mu, and the variance, which we just worked out, is equal to sigma squared by 3, right? And mu2 hat, which is again a linear combination of independent normal variables, is normally distributed with mean mu, and variance we just worked out is 3 sigma squared by 8. Okay, so that completes question 1. Alright, now let's move on to question 2. let me try to zoom in. Alright, here you have two sample means from sample sizes N1 and N2 from a normal distribution, and sigma is known but mu is unknown. So we have this following estimator for mu. The first part is to show that the bias is 0. The second part is to find the minimum of the variance and to show that it's minimized when A equal to this. Right. Okay. Sorry guys. So this is question 2. The first thing you must realize is that because x bar 1 is a sample mean of a sample of size n1 from a normal distribution, using one of the properties I mentioned in the video on normal, it will have a normal distribution with parameters mu and variance equal to sigma squared by n1. So if you don't know where this comes from, just please look at the video on normal distribution. And similarly, this x bar 2, which is a sample mean of a sample of size n2 from this, right, will have a normal distribution with these parameters. Okay. Now we have this estimator mu hat, which is 8 times x bar 1 okay. Now we want to show that this is biased. Okay, so to show, let's see how we can do that. So we want to find the bias of this, which is okay, and take the expectation inside. You have this. Okay. Now we know that x bar has this distribution, so the mean is mu. And similarly, it's also mu. And this is clearly equal to mu minus mu, which is 0. So that completes the first part. We have shown that the bias is 0 for all values of A. Right, the second part is to show that the variance is minimized when A equal to n1 divided by n1 plus n2. So let's see how we can do this. So we want to find the variance of mu hat, which is the variance of now taking the variance inside, we have a squared times the variance of x bar 1 plus 1 minus a squared. Okay. Now this guy is, we know from statements that the variance of this is a squared times sigma squared divided by n1. Sigma squared divided by n2. Okay. So this becomes Okay. Now, what we want to do is we want to minimize this. This is a function of a. We want to minimize this as a function of a. Alright, so let's call this, just for the sake of notation, let's call this a function, say g of a. Alright, so I'm calling this g. Now I want to minimize g of a as a function of a. I'm sure you've done lots of calculus, and in order to minimize a function, the first thing you need to do, so we have, okay, let me write it down. G of a equal to a squared this. Right, the first thing you need to do to minimize this is to find the first derivative with respect to a, which is 2a divided by n1 minus 2 times 1 minus a divided by n2. And you set this to 0 and solve for a. So this implies that a divided by n1 is equal to 1 minus a divided by n2. Okay? So this implies that a times n2 is equal to n1 minus a times n1. So this implies that a is equal to n1 divided by n1 plus n2. Alright, so this is the solution of the equation that the first derivative is equal to 0. To make sure that it corresponds to a minimum, right, we need to find the second order derivative. So we find the second order derivative of g, which is the first order derivative of this, right? So it's going to be 2 by n1 plus 2 by n2, which is clearly a positive number. So since the second order derivative is positive, g of a is minimized at a equal to n1 divided by n1 plus n2. And this implies that the variance, because remember the variance is g of a times sigma squared. So hence the variance of mu hat is minimized at a equal to n1 divided by n1 plus n2. Okay. Alright, so this completes question 2 of the tutorial sheet 8. Right. Next question is this one. So here we have a random sample from a distribution, but this as the PDF. Show that x bar is a biased estimator of delta. Right. Let's see how we can do this. Part 1. So we have x bar as an estimator. So we need to show that the bias of x bar is different from 0, right? To find the expected value of xi, you are given the density function, which is this one. So to find the expectation, you just need to integrate x times the density, right? So we integrate from delta to infinity because you see the range of x is greater than delta, right? Okay. This is where your calculus comes in. I'm sure all of you guys are experts in calculus, so let's see how we can do this. Right, now to do this kind of integration, I mean there are several ways you can do this integration. One way is to use parts, integration by parts. Okay, so let's see how we can do that. Alright, so using parts, this is what you get. Okay. All right. So I use by parts, integration by parts. Okay. Right, now the limit at infinity is 0. The limit at delta is minus delta e minus delta. Okay, now the integral of this is not difficult. It's simply minus of e of minus x, limits from delta to infinity. Okay. So this is going to be delta e minus delta. At infinity it is at, then you have minus e of minus delta. Okay. Okay. Alright, so this e of delta cancels out with this, so we get 1 over n times the sum 1 to n of delta plus 1 minus delta. Alright, so this is 1 over n times delta plus 1 minus delta, which is delta plus 1 minus delta, which is equal to 1, which is not equal to 0. So hence we have shown that x bar is a biased estimator of delta. Okay. Alright, so that completes the first part of question 3. Let's move on to the next part. Derive an expression for bias, right? Which we have already done that, and discuss what happens to its value as n goes to infinity. So we have already derived an expression for bias. So question 3, part 2. We have shown that the bias of x bar is equal to 1. So as n goes to infinity, it doesn't make any difference, because if you take the limit as n goes to infinity, it will still be equal to 1, because it doesn't depend on n. Right? Right. Part 3. Part 3 is can you propose an alternative unbiased estimator of delta? Yes, we can. Or yes, you can. Because if you look at these guys here, if you look at the derivations here, we have shown here that basically the expectation of x bar is equal to delta plus 1. Right? Now, you want, for the estimator to be unbiased, you want the expectation to be equal to delta, not delta plus 1. So a new estimator for delta can be defined like this. Let me call it, say, delta 2 hat, right? You can define it as x bar minus 1, right? Now I will show you that this estimator has bias equal to 0 because of the following. Alright, this minus this, which is the expectation of x bar minus 1 minus delta. Now we showed from part 1. From part 1, we know that this guy is delta plus 1. Alright, so and this is 0. Alright, so this implies that the new estimator is unbiased. Right. Okay, guys, so that completes question 3. Right. Okay, next, question 4. We have a random sample of size 5 from this. Write down the likelihood function for this data. That's the first part. The second part is, you have the following data, right, where p is unknown. And suppose that the p can take only these different values. And which of the possible values of p would be the maximum likelihood estimator for the above data? Alright, let's first do the first part, right? So let's do the first part first, and then we can talk about the second part later on, right? Okay, so okay, right, so here we have, this is question 4, part 1. Remember, we are talking about a binomial distribution with parameters 3 and p. Okay, so the likelihood of p is the product from 1 to 5, because you have 5 data points, of the density of the PMF of the binomial, which I'm sure you guys know is 3. Your m is 3. Choose xi, p power xi, 1 minus p power 3 minus xi. Alright, this is what you get. And we want to simplify this. Let's see how we can do this. So this is gonna be the product, I from 1 to 5, Yeah. Now the product of this can be written as P right, and the product of this can be written as right. Now the sum of 3 minus I from 1 to 5 is 15 minus the sum of xi. Okay. So this is the answer to part 1 of question 4. Right. Okay. Now let's move to the second part. So here you are told that you are given the values for, can you see this now? Right, you are given the values for x1 to x5, which are the following. So this is part 2. So you are told that x1 is 1, x2 is 3, x3 is 2, x4 is 2, and x5 is 3, right? Okay. And we are also told the possible values for p can be one of these numbers, 0.5, 0.6, 0.7, or 0.8, right? Okay. Now, okay, before we go ahead, let's try to sum this number. So it's 1 plus 3, 4 plus 2, 6 plus 8, and 11. So the sum of these numbers is equal to 11, right? Now, if you go to the likelihood, which I wrote down in the previous part, well, this is the likelihood I have written earlier. So your likelihood function of p will be the following. It will be 3 choose 1, 3 choose 3, 3 choose 2, 3 choose 2, 3 choose 3, then p power to 11, and 1 minus p power to 15 minus 11, which is 4. Alright, okay, so you can, let me take this away now, so you can figure this out. 3 choose 1 is 3, 1, 3, 3, 1. Okay, so this is 3 cubed, which is 27. So what you have is 27 times p power this, power this. So this is your likelihood function. Now what we need to do is we need to calculate the value of this so we need to create a table. You need to create a table where p can take the possible values 0.56. So p can take the values 0.5, 0.6, 0.7, 0.8. Now over here, I'm going to work out the value of this at these values for p, and you will get the following. You can check my answers. When p is 0.5, you get 8.24 times 10 to the power minus 4. For 0.6, you get 0.7 you get and for 0.8 you get 3. Okay, so these are the likelihood values for the 4 different values for P. Now the question is, which one is the maximum likelihood? Remember, the maximum likelihood estimator is the value for P that maximizes the likelihood value. So in this case, the largest of these 4 values for the likelihood is this one. This is the largest value. So the corresponding P is 0.7. Alright? So hence okay, so remember, the maximum likelihood estimate is always the value for the parameter for which the likelihood takes the largest value. So in this example, the likelihood is largest when P is equal to 0.7, and therefore P equal to 0.7 is a maximum likelihood estimate of P. Right? Alright, so that completes question 4. Alright, next question 5. So here we have a random sample from a geometric distribution with parameter P. Part 1 is to write down the likelihood and the log likelihood. Part 2 is to find the maximum likelihood estimator for P. Right. Okay, let's see how you can do this. Excuse me. You can see it now. Okay. So this is question 5, part 1. So we want to find the likelihood function for P when you have a random sample from a geometric distribution. So remember, the probability mass function for a geometric is this. Okay. So taking the product of this, you get this, right? And this is B power n. Now this you can write as the sum of xi, I from 1 to n, and it minus the sum of 1, which is n. Okay, so this is the likelihood function. Now the log likelihood function is just the log of it. Okay. Okay, so this is the log likelihood function of P. Right, now the second part of the question is to find the maximum likelihood estimator for P. Alright, to find the maximum likelihood estimator, as I explained in the videos, right, the first thing you need to do is to take the derivative. So this will be n over p then you set this to 0 and solve for p. Alright, so this will become okay, so this becomes n minus np equal to p times the sum of xi minus np. Alright, so the solution for p is n divided by the sum of xi, which you can also write as 1 divided by the sample mean x bar. Okay. Now, to make sure that this is an MLE or maximum likelihood estimator, we need to show that the second order derivative is negative, right? Okay, so let's see how we can do that. So you find the second order derivative with respect to p, which is the first order derivative of this. And this term will be negative because of the minus here, and because of the minus here, and also because this term here is non-negative, right? That's because this term is non-negative. This term here, let me circulate here, is non-negative. Right, because by definition of the geometric distribution, xi is greater than or equal to 1. I mean, the smallest possible value for xi for a geometric variable is 1, and this implies that the sum of xi is greater than or equal to the sum of 1, which is n, right? And this implies that the sum of xi minus n has to be greater than or equal to 0, right? So hence what we have shown is that we have shown that the second order derivative, right, is less than 0, right, and hence the estimator that p equal to 1 divided by x bar, right, is the MLE of p. Alright, so that completes question 5 of the tutorial sheet. Now the next question, let's go there, this one, question 6. So this question is on some confidence intervals. Let me zoom in. Sorry. So here you have that measurement error is normally distributed with the standard deviation sigma, right? You have a sample of 10 observations, which are this, and calculate 95% and a 99% confidence interval for the PCB level, right? So let's see how we can do this. So this is question 6. Excuse me. So here you're told explicitly that the value for sigma is 0.8 and your n is 10, which are these data points. Now if you look at my video or the notes on confidence interval, now we are looking for confidence interval for the population mean, which is mu. So under these conditions, the confidence interval let me see, 100 times, this is the notation I had used, 100 times 1 minus alpha % confidence interval for mu is the population mean, is, if you look at the notes, is the following: is x bar is the sample mean, plus or minus this is the, if you look in the video or the typed notes or the handwritten notes, you should be able to see this formula right from the course website, right? So this is the formula that I had given you. So all we have to do is to use this, apply this formula for this particular question. So for the first part of the question, we want a 95% confidence interval. So in other words, 100 times 1 minus alpha is 95. So that implies that your 1 minus alpha is 0.95 and your alpha is 0.05. And your Z, this is the percentile of the standard normal with the probability of 1 minus alpha by 2. It's gonna be 1 minus 0.025, right? And if you read that of the table, if you read the value, or if you read this value of the normal table, I showed you how to do that in the video. If you read this off the table, you will get this to be 1.96, right? And your sigma is already given, it's 0.8, n is given, x bar is the sample mean. So it's basically the average of these 10 different values, right? So that is, if you compute that, you will get it to be 11.48. So hence the 95% confidence interval is 11.48 plus or minus 1.96 multiplied by sigma divided by root of n. Alright, so this is the 95% confidence interval, and you can, if you have a calculator, you can simplify it. This will become 10.99, 11.98. Alright. Okay, so that's part 1 of question 6. Now part 2. we want to find the 99% confidence interval. So we want 100 times 1 minus alpha to be equal to 99. Alright, so one minus alpha is this. So your alpha is this, and so your z is this, yeah, and this is z 0.995, and if you read this off the table, you will get 2.576. So hence the 99% confidence interval for mu is 11.48, which is the sample mean, plus or minus 2.576 multiplied by sigma divided by square root of n. Alright. Okay, so this, if you do the math, you will get this to be equal to 10.83 and 12.13. Alright, so this completes second part of question 6 and question 6 too. The final question on this sheet is question 7, right, which is this one. Here you're given a standard deviation of 3.4, a sample size of 9, and you're told that the average lifetime is 100.8 hours, so x bar is 100.8. And you're asked to find the 95% and 98% confidence interval for the population mean. So let's start with the first part. So you want the 95%. Alright, so 100 times 1 minus alpha is 95. So your 1 minus alpha is 0.95. So your alpha is 0.05. And this is 1 minus 0.025, and this is this, and this is equal to 1.96. So if you read off the table that I gave you as part of the video, this will be 1.96. So hence the 95% confidence interval is 100.8 plus or minus 1.96 times 3.4, which is a sigma, divided by root of n, which is root of 9, which is 3. So if you work this out using a calculator, you get 98.58, and the upper limit is 103.02. So that's the first part. The second part, we want a 98% confidence interval. So 100 times 1 minus alpha is 98. So your 1 minus alpha is 0.98. So your alpha is 0.02. And your z 1 minus alpha by 2 is z 1 minus 0.01, which is z 0.99, and if you read this off the table, you will get 2.3263. So hence the 98% confidence interval is 100.8 plus or minus 2.3263 times sigma, which is 3.4, divided by root of n, root of 9. Now if you compute this using a calculator, this is what you will get. You get 98.16 103.44. Alright, so this completes the solution to question 7 and also completes the solution to the video solution to tutorial sheet 8.